Alright, so functions are more than two variables. So say now we have a function with more than two independent variables. So we have a function of x, y, and z as independent variables. I'm not going to ask you to ever draw that. I mean, imagine having some type of object in a four-dimensional space that's defined with three independent variables. You're not gonna. It's really, you're not really going to be able to see that, and it's just very rarely would I have you do one like this because what's going to be that fourth dimension? Again, we've mentioned that some scientists call it time, and that would be how we're going to be able to conceptualize this. But for the most part, we're just going to be dealing with with the three-dimensional coordinate system. So, but we're saying the same rules that applies to the three-dimensional coordinate system, and they're going to apply to the four-dimensional when we're talking about. Sorry, that was my alarm to wake me up to do the notes. I woke up a little bit earlier. So the same rules are going to apply for partial derivatives with, three independent variables. Where if we're taking the partial derivative, say with respect to one of those, like x, then the y and z variables are just going to be treated as constants. And so that's, the only thing that, it's not really different, it's just you have an extra variable to deal with, right? So now, example 6, we have three independent variables for this function x, y, and z, and we want to take the derivative here. It looks like x, but I want you to notice that this is taking the partial with respect to z. All right, so that these notes are not, they got a bunch of marks on them this time, so I'm sorry about that, but we're taking the partial with respect to z. So if we're taking the partial derivative with respect to z, we're going to get 1/2 sine squared x plus sine squared y plus sine squared z times, raised to the negative 1/2 times the derivative of sine squared z, which is 2 sine z cosine z. All right, now we're going to go ahead and rewrite this because the 2's are going to cancel each other out. So I'm just going to say sine z times cosine z over the square root of sine squared x plus sine squared y plus sine squared z. Now we can go ahead and substitute in our x's, y's, and z's. So we're going to get sine of pi over 4 times cosine pi over 4 over the square root of sine squared 0 plus sine squared 0 plus sine squared 0. Not 0, pi over 4. Alright, well, sine of pi over 4 is just square root 2 over 2 times square root 2 over 2 over 0 squared plus 0 squared plus square root of 2 squared, so square root of 2 squared. And I'll just move my work down here. Alright, so square root 2 times square root 2 is just going to give us 2 over 4, and that will reduce to 1/2. In the denominator, I'm going to go ahead and square the top, which is just going to be 2 over the bottom. So that's going to give me 1/2 divided by the square root of 2 over 2, which is just going to be 1 over square root of 2, and we're finished there. Or you could rationalize